Wow, what do we have? 8 people in class today? This is like our best attendance since the first day of class. I didn't know regression was that exciting. Anyway, I guess I'll take advantage of the fact we've got more people here today. I need to get assignment 4 put together and send out an email, but just so that everybody's thinking about it, I'm debating making a change to the syllabus that either scrapping the final exam or making a much shorter final exam and replacing it with writing an NIH R03 or R21 application. It's the sort I love the way like people go up this excited face to a really scared face. I mean, I'm not married to this idea at all. If it's a terrifying idea, I won't do it. But I mean, just trying to be relevant to the bench scientists who are most of this class. Grant writing is one of the single most important things you do if you become a faculty member, and it's something that just does not get taught in our curriculum. So, I mean, I will be generous and only grade harshly on the statistical parts, but the point would be just so that you know, like, you're not like me, that in your first faculty interview, they're like, so when are you going to write your first R01? You're sitting there like, write my first what? That's a what? Yeah, it's bad. Anyway, I'll send out an email, like I said. Feel free to send me emails with comments if you think this was good or bad one way or the other. I mean, if most people don't like the idea, I won't do it. This is just my way to try to make the class more relevant. Anyway, so for today, regression. Recall the point of regression is if you have 2 quantitative variables and you want to talk about the association between the 2 variables. That is an association between variable A and variable B statistically significant, more strong than we would expect to observe by chance. How strong is this association, and can we predict one variable based on the value of the other variable? And regression, to me, is one of the most important methods in statistics, so we'll be devoting probably slightly over 2 weeks to this. So you'll probably get really sick of it soon, but I find, other than like maybe t-tests and chi-square tests, it's the technique that I use the most, and it's probably useful in the widest variety of circumstances. You'll see a lot of the other tests that we've considered in this class are just special cases of regression. If you master regression, you master about 70 to 80% of what you need to do in statistics, hence the reason that I beat this horse to death. The basic idea of what we're trying to accomplish in regression in the simplest case is on this plot here. You'll recall this example from Monday where we're trying to predict the stopping distances of cars versus the speed of the car at the time they stopped, and this data is from the 1920s, so brakes weren't as good back then. But the objective is, there's several possible objectives here. One is there an association between speed and stopping distance? I mean, our intuition says that there should be, aside from the math, but it would be nice to be able to do some sort of test to see if this association is statistically significant. And the related question is, if you have a car going at a certain speed, what's the best possible prediction of the stopping distance of that car when you slam on the brakes? So today I'll give a brief overview of how you would answer these questions. So, quick review of just lines and linear functions in general. If you remember your college math classes, then you can just sleep through the next 5 or 10 minutes or so. But just in case anybody needs a quick refresher course in this, linear function, so-called a linear function because if you graph the function, it's a straight line, as I'll show you here in a second, is just any function of the form where you have some response variable equal to A plus B times a predictor variable. A simple case, say you have like an old school amusement park. It costs $10 to get into the park, and it costs $3 for each ride you go on. So the total cost of your day at the amusement park would be equal to $10 plus 3 times the number of rides that you go on. That would be a linear function. And looks like Keynote did wonderful things to my table again. Hopefully the PDF and PowerPoint files on Sakai look better, but if you can sort of read this table, it's just a table showing the total cost for different values of rides. If you go on 0 rides, it costs $10. If you go on 1 ride, it's $13. 2 rides, $16. And yeah, probably don't need to say much more to that because I'm insulting your intelligence already. Anyway, in terms of terminology, if a general linear function would be y equals a plus bx, in this case, a would be $10, b would be $3. The cost of a single ride. Terminology, in case you've forgotten this from your last math class, the variable a in this case is called the y-intercept. The variable b in this case is called the slope, which I think I have a graph. Yeah, here's a graph on the next page which illustrates why these variables have their names. First of all, y-intercept, in this case, I plotted this in R, which doesn't have the traditional convention where you have an x-axis and a y-axis starting at 0. If we did the traditional convention in math where you had a y-axis going up and down, or a y-axis going up and down where x equals 0, then you would see that y is equal to 10 at the point where x is equal to 0. In other words, the line would intercept the y-axis at y equals 10, hence the reason 10 is known as the y-intercept. It's where it intercepts the y-axis if you do a traditional graph. And the slope of the graph means that for every 1 unit you go to the right on the graph, you go up 3 units. So a slope, as its name implies, gives you something of a measure of the steepness of the graph. A slope of 0 would be a horizontal line. The higher the slope, the steeper the graph is. And if you ever need to fit the equation for a line for this class, you won't, but just for the sake of review, because it helps understand some of the intuition behind regression, the standard equation for the slope is, as they say, rise over run, or like the change in y divided by the change in x between any 2 points on the graph. So in the case of our amusement park function, if you have the points 0, 10, 1, 13, to get the slope you can take the difference in the y's, that is 13 minus 10, divided by the difference in the x's, i.e. 1 minus 0, gives you a slope of 3. And once you have the slope, you can calculate the y-intercept using any point in the graph, just using algebra, that if you know the line passes through the point 1, 13, you know that b is equal to 3, you just substitute in x, y, and b and solve for a. So 13 equals a plus 3 times 1. Simplify, get a equals 10. Hopefully nothing here too shocking to anyone, and even if anyone is rusty on this, it's not something you'll really need to use much for this class. It's just as a quick reminder of how these regression functions work. So, as I said, the interpretation of slope is that a 1 unit increase in x is associated with a b unit increase in y, or if b is negative, then it's associated with a b unit decrease in y. So the amusement park function is once again a 1 unit increase in the number of rides associated with a $3 increase in the total cost of the day at the amusement park. So Well, that's nice and good. Now let's go back to the case of linear regression. Let's take our stopping distance data set. Let's say that we have this set of data points on the stopping distance of cars at various speeds. We want to try to predict as accurately as possible how long it's going to take the car to stop if you slam on the brakes at a given speed. How would you go about doing that? Well, okay, first of all, the first question we need to answer is, we say the best possible approximation to stopping distance given speed, or more generally, the best possible approximation of y given x. What do we mean by that? How do you define a line that does a good job of approximating the data? Well, the way that this is conventionally done in statistics is you try to find a line that minimizes the sum of squared errors. That is, you find a line, you find values b0 and b1, and then approximate y as b0 plus b1x, so as to minimize the difference between the predicted values and the actual values squared. To give an additional illustration of what that means, say you have a regression line that looks like this. The line indicates the predicted values of y, the dots indicate the actual values of y, and each of these numbers gives the difference between the predicted value and the actual value. It looks like for x equals 4.5, the predicted value is around, I don't know, 2.7, the actual value is around 2.9, the difference is 0.2. Likewise, the difference here would be minus 0.22, difference here is 0.33, etc., etc. So the sum of squared errors in this case would be 0.2 squared plus minus 0.22 squared plus 0.33 squared plus 0.21 squared, and so on. Add all those up, you get the sum of squared errors. The regression line is the line that makes that sum of squared errors as small as possible among any possible sets of lines that predict y based on x. And I guess I could editorialize on that a bit further. Why do we minimize the sum of squared errors? Really, honestly, truly, it's because it makes the math easy and makes it so that there's a pretty formula for the slope and the y-intercept in this case. I mean, minimizing the sum of squared errors has certain drawbacks I'll discuss here in a minute. In particular, it's not robust against outliers at all, and just a single outlier can mess up your regression line really bad. And people have experimented with other forms of regression where you try to minimize the sum of the absolute value of the errors rather than the squared errors. I'm not going to go into that in this class because, number one, basically almost nobody uses it, and number two, it's so hard to make any decent inferences from that case that it's just not worth bothering with, in my opinion. In practice, basically everyone uses the ordinary least squares regression, as it's called, I'm giving you the formula for right here. And basically, the formula for the least squares regression line is this right here. Call x bar is the mean of the x's, y bar is the mean of the y's, s sub y and s sub x are the standard deviations. You will never need to use the equations on this slide again. Now that you've seen them, it's a complicated mess that I would never ask you to do by hand, but just in case you ever needed the exact formula to do this for some horrible reason, there it is, but for this class we'll just use R for all of it. Oh, how do you calculate regression lines in R? The command to do this is called LM, which stands for linear model, and it takes a formula object. Remember the little twiddle in R. As I told you before, we were going to see this again. In particular, regression is where you use formula objects more than anything. You say LM distance twiddle speed. That says fit a regression model to predict stopping distance based on speed. I say data equals cars. That tells R that these two variables will be columns from the cars data frame, which is built into R. If I had done attach cars before I ran this command, I wouldn't have needed to say data equals cars. Likewise, I could have gone LM cars $distance twiddle cars $speed. All of those work. In this case, I just used the data object to avoid that. And if you save the output of the LM command in a particular R object, then do summary cars.lm, it gives you a bunch of output that a lot of this I'll explain in more detail on Friday, so you don't need to worry too much about this right now. The important things for today are this column here that says estimates. Intercept is the estimated y-intercept for regression, and speed is the estimated slope. So in other words, the regression line to predict the y-intercept, or the regression line to predict the stopping distance based on speed, would be stopping distance equals minus 17.58 plus 3.93 times the speed. And for the record, this p-value here is for testing the null hypothesis that the slope is equal to 0. In this case, it's ridiculously tiny, so there's very strong evidence against the null hypothesis that the true speed is 0. And like I said, I'll cover that in more detail on Friday. The reason that's important is, as I said, if you have two quantitative variables and you want to test the null hypothesis of no association between the two variables, then this would be the p-value that you would want to test. In this case, the null hypothesis would be that the speed when you hit the brakes has no effect on the stopping distance. There's very strong evidence against that null hypothesis. And the rest of these measures down here are measures of how well the regression line fits the data. As I said, I'll cover that all in more detail on Friday. And in general, as I've noted in earlier lectures, if you have y twiddle x in R, that's a formula object. It says you want to try to predict y based on x. In this case, we're trying to predict stopping distance based on speed. If you say LM y twiddle x, that means fit a regression model to predict y based on x. And if you say LM y twiddle x, data equals whatever, then that says that y and x should be columns of the data frame that you call data set, so that you don't have to do data set $y, data set $x, or whatever the case may be. And a couple other functions in R that are useful when messing with regression. One command called coef gives the coefficients for the regression line. If you didn't want to wade through all that output from the summary command, you just wanted the regression coefficients so that you could report them, you can say coef cars.lm, you get minus 17.58 plus 3.93 times speed. Same thing that we got from the summary command. And this function fitted cars.lm, that gives the predicted value of the stopping distance for each possible value of the speed. So I would have to print out the list of speeds in this data set, which I didn't do here. I think the lowest speed was pretty close to 0. It gives the predicted stopping distance for each of the speeds in the data set. oh, if you wanted to use your regression line to predict the value of y for the x's to use to fit the data, that fitted command will do it. And yeah, I already said most of this. Coef lm.object will give you the coefficients of a regression object. Fitted of an lm object will give the fitted values, that is, the estimated value of y for each possible value of x. And another thing you may be interested in with regression models are what's called residuals. Residuals are basically the error in your model, that the residual of an observation is the difference between the actual value of the observation and the predicted value. In mathematical terms, if the actual value of y is yi and the predicted value of I is yi hat, then the residual is just yi minus yi hat. And if we have a quote-unquote good regression model, then you'll expect the residuals to be small with no noticeable patterns. And honestly, if the objective is to make predictions in the future, the no noticeable patterns may be even more important than the small criteria. Well, once again, this is another thing that we will discuss in much more detail in coming lectures. And to calculate residuals in R, the command is called Resid. And in this case, this is the difference between the predicted value of y and the actual value of y for each item in the car's data set, or for each observation in the car's data set that we fit the regression model to. Yeah, as I said, this is just sort of a preview of coming attractions. In the next few days, we'll be discussing all the things that you can and should do with residuals to see if your model's working the way it's supposed to. Yeah, in general, just resid lm.object gives you the residuals of regression object. Straightforward enough, hopefully. So, like I said, all of this we'll discuss in more detail later, but in your ideal regression model, you have like y equals b0 plus b1x plus noise, and this noise is just completely random with no pattern whatsoever to it. So if you plot your residuals, they should just look like random noise. If you plot your residuals and you see a pattern in your residuals that indicates that your error is non-random, there's probably some systematic error that your model isn't capturing, which may indicate there's a problem with your model. Likewise, if you see a really big or a really large positive or large negative residual, that indicates that you may have an outlier in your data set that's influencing your regression model. We'll discuss all of this in more detail in a later lecture. If you want to make predictions based on a regression line, you just kind of do the obvious thing. If, say, you have a new value of x and you want to predict the value of y, you just take the new value of x, plug it into your regression equation, and your predicted value of y will just be b0 plus b1 times x, where x is whatever value of y that you plug in. And if you want to make predictions in R, there's two ways that you can do this. One way is the obvious way. You just extract the coefficients. Recall, if we do coef cars.lm, we get our first coefficient of about minus 17.58, our second coefficient of 3.93. So if we wanted to predict the stopping distance when speed is 21 miles per hour, we can take minus 17.58 plus 3.93 times 21. we get a predicted stopping distance of about 65 feet. The other way you can do this in R is with the predict command in R. Unfortunately, the syntax for this is a little bit clunky. There's a good reason for this, because when we do multiple regression, you kind of have to do it this way. But when you're just doing a simple linear regression with one y and one x, the predict function is a big headache. I always want to say predict cars.lm, then just say new data equals 21. If you say that, R will blow up and give you an error. The correct syntax is right here. The new data has to be a data frame, and it has to have a column with the same name as your x variable in the model. In this case, the x variable in our model was called speed. So to get R to make a prediction when speed is equal to 21, you have to say predict cars.lm, then new data equals data.frame, speed equals 21. Like I said, clunky, sorry about that, but there's no simpler way to do it, unfortunately. You see, when we do it that way, we end up with a predicted stopping distance of 65, exactly the same number that we got when we just plugged the x into the model manually. So, in general, if you go predict lm.object new data equals data, that will make predictions for a regression model at whatever points in the data frame that you call data, and this data has to be a data frame. If you want to make a prediction for a variable called x, you have to do something like predict new lm.object new data equals data.frame, x equals x0. Like I say, it's just one of those idiosyncratic R things you just have to learn and deal with, unfortunately. And just some general philosophical stuff about making predictions based on regression models. We make this distinction between interpolation, which means that you predict within the ranges of x's that you use to fit your model, and extrapolation is to predict outside the range of x's that you use to fit the model. And extrapolation can be hazardous if you didn't see the comic already, that this woman got married today, so yesterday she had 0 husbands, today she has 1 husband, so if she extrapolates, by the end of next month she will have 50 husbands. That illustrates why extrapolation can get you in trouble. And it's very common for data to have an approximately linear pattern for part of its range, a different pattern elsewhere. Just like the stopping distance example that I've been using, as I remember from physics class that the true association isn't really linear so much as exponential, which for sufficiently small values is approximately linear. But it illustrates that if you take some 1920s Model T and take it up to 80 miles per hour and slam on the brakes, the stopping distance may be significantly greater than what's predicted by this regression model. That, hence, it should be avoided. That, I mean, as I recall, a famous example of this, which I didn't use in this class, partly because it will just make me feel older than I do already, that there's a famous example in these regression classes of like the O-ring data from the Space Shuttle Challenger, and basically they were trying to predict how, like, I forget the details, like how much heat these O-rings could take before they failed, and they just kind of extrapolated based on the data, and the extrapolation was not valid outside the range, and yeah, led to the Challenger disaster. Aside from the fact that's a semi-morbid example, it's like occurred to me that most of you probably weren't even alive when that happened, and hence may not be the most relevant example, and I just like already feel like I should just fossilize myself or something. But in any event, if you extrapolate, when you write your paper, you should clearly say that you're extrapolating and indicate what assumptions you're making with the extrapolation, and also do a major cost-benefit analysis of what happens if your extrapolation turns out to be wrong. If it's like your extrapolation is incorrect and that causes the space shuttle to blow up, probably best not to be extrapolating. And a couple other quick notes on regression, that if you reverse the x's and y's on your regression, if you fit a new regression line to predict x based on y rather than predicting y based on x, in general you'll get a different regression line. The slope will not be the same, although it will have the same sign, and regardless of whether you're regressing, and in both cases the regression line will always pass through the point x bar, y bar. Once again, I lost the bars when I converted this to keynote, unfortunately. And another important note is that linear regression is not robust, as I'll illustrate here in a second. That this is another thing that we'll discuss in more detail in an upcoming lecture, but just in preview of coming attractions. In regression, we talk about outliers and influential observations. Outliers are data points that fall outside the overall data distribution, and influential observations are data points that will change the regression line quite a bit if removed. Now, most of the time outliers are influential, most of the time influential observations are outliers, but they're not necessarily synonymous, as I'll discuss later. For the time being, the biggest thing to keep in mind is that you always want to graph the data to see if the patterns picked up by your regression line may be due to a small number of a single outlier, a small number of outliers, or something like that. Here are examples of potential outliers in your regression model, that it illustrates that it's also not simple to define outliers in the context of regression. You have both an x variable and a y variable, and you can have outliers with respect to one or both or neither. Here, in this first graph, you see an example of x equals 30 is an outlier with respect to x. It's within the normal range of the y's, but with respect to x, it's an outlier. Likewise, example 2, you have a data point that's a major outlier with respect to y, but there's nothing unusual about the corresponding x. Example 3, you have an outlier with respect to both x and y. Example 4, you have a data point that's a clear outlier, but if you just looked at the distribution of the x's or the distribution of the y's, just did a box plot of each one separately or something, you wouldn't see it because it's not particularly unusual with respect to the distribution of either possible variable. So, main take-home message, whenever you do regression, it's good to do a scatter plot or something like this just as a sanity check to see if there's outliers that are driving your regression line one way or the other. As we'll discuss later on, interestingly enough, it's actually usually these outliers with respect to x that get you into major trouble. Outliers with respect to y are problematic as well, but it's the x ones that usually cause really major problems. Like I said, all of this we'll discuss in more detail later. And when we talk about influential observations, that this is just to illustrate that influential observations and outliers are not necessarily synonymous, that here we have a data point that's something of an outlier because as an extreme value of both x and y up here in the upper right-hand corner, but it still fits the pattern of the regression line almost perfectly. Recall an influential observation is an observation that causes a big change in the regression line if it's removed. If we move that point in the upper right-hand corner, in this case, it actually doesn't do much to the regression line because it fits the pattern almost perfectly. Now, on the other hand, if we had a regression line that looked something like this, and then we had this outlier in the lower right-hand corner, that would be an outlier that's also highly influential. The black regression line in this plot is the line. If we exclude that outlier, the red line is what happens if the outlier gets included. You see, you just have one strange data point in your data set, and it can have a big effect on your regression line. That's why I warn you about regression not being robust. And it's very easy to construct examples where there's no association between x and y. For the vast majority of your data, you get one weird data point with a large x and a large y, and it will create a positive slope that's significantly different from 0. So graph your data, don't just apply regression mindlessly and report the p-value without looking to see what's actually going on. So, outliers can really mess up your regression line. You always want to plot your data to try to find outliers, and if you see data that looks problematic, then you want to remove it if you think the data is bad. And later, in a couple of days, I think one of the first lectures after spring break, or it might be Erica, because I might be out of town, will devote an entire lecture to this on ways to identify outliers and influential observations and remove them if necessary. So, things to remember for today. Using regression, you can predict an outcome variable y, using a predictor variable x, using linear regression, and you don't want to extrapolate outside your data if you can avoid it, and if you do so, do very cautiously. And regression is not robust against outliers or other types of extreme values. Make sure you plot your data and make sure to see if anything is going horrendously wrong in that case. R commands to remember for today. LM y twiddle x gives you a regression line. Then you can use COA fitted Resid to get the coefficients, the fitted values, and residuals respectively, and then predict if you need to predict values of y for new values of x. Any questions about any of this today? Okay. Well, I guess there was one other announcement that I forgot to make at the beginning of class that I'll also put in the email today, that Erica wanted me to ask about Friday's discussion section, that, like, if people have questions and want to come to discussion section, she is very happy to teach it. I mean, I may even make an appearance myself if I'm not busy, but she was just kind of thinking, like, 3 o'clock the day before spring break starts. We haven't exactly been getting a huge turnout for the discussion section in the best of time. They're guessing that, like, most people 3 o'clock before spring break starts, they don't really want to do statistics. So, basic question, if you were planning on coming to discussion section on Friday, send me an email. If at least one person's planning on coming, we'll hold it. But if nobody's going to come, then Erica will just start her spring break early. So I'll send out an email to class about that as well.